Let's get going. We're on the threshold of chapter 7, oscillations, but probably we'll start that on Tuesday. So in addition to the regular homework, which I'll mention at the end of class before we dismiss, you can start skimming chapter 7. Skim ahead. Start reading that on oscillations. Last time we discussed heat transport. Get your clickers ready. We're going to click in a few minutes. And we talked about the 3 transport modes for heat energy. First one, conduction through thermal contact. And we talked about convection, the bulk motion, a good example of which is just a hot air balloon. You fill it up with hot air, and it won't work on a really hot summer day, but on a cool morning like we had today, it probably worked fairly well. And I'm going to have to try a hot air balloon ride one of these days. Another convection system, of course, you probably know this, thunderstorms, tornadoes, and hurricanes. Hurricane is a huge organized convection. You guys all squared away? Sedora? You're all good. Good. Now, what we were talking about at the end of class was radiation transfer of energy. And let's talk about that in detail, because we didn't have quite enough time to do that. An example of radiation moving heat from point A to point B is like the space program. You get, those guys up there in like the Apollo mission, when they're halfway between the moon and the earth, they're out there in space and there's no shade. They're not going around the shady side of the earth or the shady side of the moon every orbit. They're just, out in the middle. So they get a lot of solar heat gain out there. And they have to defeat that. There's various ways to do it. We're going to talk about some. So they get a lot of positive Q from solar energy. So all the sunlight, so from infrared and radio waves, they're not going to have a huge effect. The infrared will. But all the way up to ultraviolet, that'll heat up a spacecraft if you're out there. Now, if you're on the shady side of the earth, on the night side of the earth, did you realize that at this minute, it's almost noon in Orlando, that there's a place on earth that's night? Did you realize that? And it happens every day at this time. Somewhere on the earth, it's 10:38 p.m. So I don't know where that would be. Like maybe I wonder what time it is in Hawaii. I don't think that 7:38. So they're 3 hours behind us. That can't be right. California is 3 hours behind us. Anyways, so you're flying around the shady side of the earth. If you're on the shady side of the earth, you gotta worry about losing energy. What's that? So Hawaii is 6 hours. So for them, it's 4 in the morning. Oh my goodness. So maybe Japan, it's 10:38 at night. In Japan? So it's 11:38 on November 1st in Japan. 11:38 p.m. Anyway, if you're on the shady side of the earth or, whatever it is, you're radiating heat into space. Here's another thing you may have noticed here in Florida, and if you ever live out west, where the atmosphere is a lot drier, so Colorado or Utah, Montana, out that way, at night, all the energy in the atmosphere, all the heat energy in the soil and the rocks, the mountains, the plants, it radiates into space. Now here we have a lot of cloud cover. So all that infrared a lot of it's reflected back. And when the clouds are out here in Florida, we don't get as cold at night. But like last night, it was, when I got up this morning, it was clear as a bell. And if you're out west and it's a clear night, you're going to freeze your patooties off, if you're out west. Now here, you're not going to get that cold. But in space, you really have to. So NASA's got to manage their solar energy budget very, very carefully. And an example of that is something that they invented for the Apollo mission, and that's what they call the BBQ Roll. And they sent the Apollo command module, to the moon, and it was also carrying the lunar module and stuff. So the whole shebang heading for the moon, and they just made it roll really slowly, kind of like something on a barbecue. And that was one of the ways that they kept the ship from getting heated up. And I'll show you a diagram of it later. Other systems like this solar hot water unit in the lower image here, that thing's you want to maximize your solar energy gain from that. So it just depends on what you're trying to do. Okay? And if something is transparent, that means it doesn't absorb a lot of light. And nothing's perfectly transparent, but glass is pretty transparent, but it's not perfectly transparent. Because glass will heat up. I mean, if you put a piece of cold glass in your car, in the morning at 7 o'clock when it's dark, the glass in your windshield and stuff, and your windows and whatnot is cold. But then if you can put your hand on it. In fact, it's got water on it. It's got condensed moisture from the atmosphere. But that doesn't happen at noon. In the middle of the afternoon, you're out here in a surface parking lot, and your car is baking, my friend. And even the glass is absorbing energy. So it just depends on what you're trying to do. Whether you're trying to defeat it or you're trying to maximize it. Or, a little bit of both like the NASA. Now, I mentioned the BBQ Roll here. Here's a blurb page from MIT. These are the guys that figured out up there at MIT at their lab how to get the Apollo command module to handle all that heat on the way out to the moon, because they're out there, they're getting a lot of heat, 1,370 joules per square meter per second from the SUN. And so they decided to invent the barbecue mode. Now I'll read this to you. Requirement for long periods of coasting flight, in other words, between the Earth and the moon, provide passive thermal control by implementing a barbecue mode, a very slow rotation, 1 revolution per 10 minutes or slower, about the spacecraft roll axis. And with the desired roll axis direction fixed in space. So they want to be able to, aim the command module at the rendezvous point. So the moon's coming in here from the right, and they're trying to, they're aimed a little bit ahead of the moon. And by the time they get out there, they'll be ready to intersect and orbit the moon. So they're out there, the moon's coming up here, and they're aimed over here, and they want to, keep going in that direction because they know that by the time they get out that 240,000 miles, they'll be, the moon will be there, okay? And so as they go, they want to aim and they want to roll. Now, take a look at this. This is also from this MIT spec sheet. A ton of calculus equations on here, and trig out the wazoo in 3 dimensions. And so don't worry about it. Just enjoy the fact that you don't have to deal with this. But there is something in here that I want you to notice. Right here. Moment of inertia, baby. And because, see, here it is right here. See that? Kilogram meter squared, bunch of numbers. But it's not just one number. And the reason it's not is because the spacecraft, the center of mass is in one place if nobody moves. So if the astronauts are in their chairs and they don't move the whole way to the moon, then there's this fixed center of mass, and but you still have a spacecraft that's not perfectly symmetric. So some oxygen tanks on the starboard side of the ship might be a little heavier than some hydrogen tanks on the other side of the ship, on the port side. All right, so it's not, and that's why the moment of inertia here is not just one number, it's 9 numbers. For every three spatial dimensions, and every roll axis that can be aimed in 3 spatial directions, you got to figure out a bunch of MR squares. Now, the guys at NASA, at Mission, well, probably the guys that designed the spacecraft, so Northrop Grumman, they calculate MR squared for that entire fantastic machine. So it probably took them a month of Sundays, but they did it. And they've got to do it three numbers for each spatial direction. Right? But we know how to do that. We did some simple MR squareds. A couple of masses. The ice skater effect, we did some MR squareds for this. It's basically the same technology. So yeah, this we got this. And they've got an asymmetrical spaceship, not perfectly balanced. But yeah, they can do it. You got to do 9 numbers instead of just 1. Like for rotation about, the hoop, for the rotation about the axis of symmetry, you have 1 moment of inertia. But if you chose a different one so that the hoop spun around one of its own diameters, then you'd have a different moment of inertia, and that would be a little trickier to calculate. But you could do it, a little bit of calculus. So don't worry about all this calculus and trig, except to think to yourself, yay, I don't have to do that. But they got, 1 revolution every 10 minutes. It's perfectly nice. Now, I want to talk about this idea of heating stuff up and getting to a thermal equilibrium. And I'll just draw your attention to the SR-71 Blackbird, which is a Lockheed jet developed in the late 50s and early 60s for reconnaissance to fly over the Soviet Union and never get shot. They shot stuff at it, but it's never been shot down because it's so fast it outflies anything else on the planet, and nobody knows the top speed of it. But the cool thing about it is you can see it at night if you're lucky, if they're flying it, because the leading edges of it will get red. It'll go so fast, you'll see the red hot, and that means that it's delta T. Like in this picture, it's it's landing. It's got a parachute out. See, it's got to use like the shuttle. It needs a parachute to help it stop because it's a high-speed aircraft. Nice piece of machinery. They're in retirement now, but like many people in retirement, they're ready to go at a moment's notice. Well, in about a month's notice, they can bring them out, start flying them again. So let's talk about thermal equilibrium and the fact that, if you have 2 different objects in thermal contact, but different temperatures, they're not in equilibrium. So what happens is, if the temperature of substance Y over here, so it's kind of like a little generic blob of substance Y, and it's in contact with another blob of substance X. So if substance Y has a higher temperature, then energy is going to flow, heat energy is going to flow from the hot one into the cold one. It never goes the other way. Energy doesn't, net energy doesn't flow from the cold into the hot. So it's never the case that something gets colder and something gets hotter. It's always the case that the cold gets warmer and the warmer object gets colder. All right? And it's basically because if you think in terms of molecular and kinetic theory, the molecules in substance Y, higher temperature, axle. So higher temperature means higher average kinetic energy. So there's going to be a lot of particles that, so here's a red, big, thick red arrow from Y over to X. There's going to be a lot of kinetic energy that's going to naturally go over there because it has a higher temperature. So afferent, it's got a higher average kinetic energy. Now, substance X has got some kinetic energy as well, but it doesn't have as much, so it's a little bit pokier. So I made this one green and a little bit smaller arrow. So it's a little wimpier. All right? So the net, if you think in terms of molecular kinetic energy, the net's going to go from the hotter object into the colder object. All right? Just thinking in terms of average kinetic energy, that's all. All right? So the thing that with the higher average kinetic energy, this is going to be a lot more kinetic because they're going faster on average. And the stuff on average in the colder object, they're going, but it's a little pokier average kinetic energy. So they're rotating probably faster than us, but they're not as big average on average as substance Y. So now, eventually, the averages will, substance X, every time it gets a little bit of extra energy from substance Y, its average goes up. It's getting a little delta T. Right? So substance X, the temperature is going to rise, and when that happens, it comes out of substance Y. So substance Y dips. The delta T is negatory for the hot one. So the hot object drops a little bit of temperature, loses some energy to the cool object. The cool object rises in temperature a little bit and absorbs that energy. All right, and that homework number 5 from homework 6, or item number 5 from homework 16 was all about that. Now, when they get to the point where the averages are the same, there's no net flow of energy. You're still getting molecules to interchange from X to Y, but the average is now such that, you're not really getting much net. And that's when you have thermal equilibrium, when the temperatures balance out. All right? Now, I want you to get your clickers ready because we're going to do some clicking questions. And it's going to be all about this idea of objects cooling and warming up. All right? So here's the diagram from number 5. What's that? I have to keep going. You can get it from YouTube, okay? Just grab it from YouTube. It'll be up in about an hour and a half, okay? So we're going to work out this problem, number 5, and we're going to take it all the way to the end. We're going to figure out the equilibrium temperature. And what you had in homework 16, number 5, was a single step, a single thought, a single idea to start calculating the thermal equilibrium temperature. For substance J and substance U, different temperatures to start and different masses. Now, I want to work through some clicker questions with you. So get your clickers out. And these are multiple choice. And they're actually kind of like almost, most of them are like true, false. You only have to choose one of two objects, one of two options. All right. So, and also I want to let you know that these next 4 or 5 questions are like notes. All right. So make a note of what we have. And by the way, I published a roundup figure for all the way up to Tuesday lecture. So now both sections are even at 50-50 until, and then after today we'll have about 55-55. All right. So you can look at your different, and you can always figure out your homework pointage. You got 2 exams, that's squared away. And now you have a new roundup number so you can recalculate your participation pointage. And since it's 50-50, that means you have 50 questions, so 85% of that is 42.5 questions. So if you have 43 answered, so if the decimal part of your roundup number is 0.43 or more, then you've got 25 out of 25. The whole number part is related to how many you have correct. That tells you the number that you have correct. So that'll be a number smaller than or equal to the number you've answered. So if you have 75% correct, and so that's 37.5 or 38, 38 or more correct in the whole number part, then that's 4 bonus points. But you don't get them yet. You don't get them today. I mean, if this was the end of the semester, but we got to go. Do you realize that 4 weeks from today will be our last lecture? It's gone fast. It's been fun too. I've enjoyed having all you guys in class. I'm just looking around. I don't see a single person that I didn't enjoy having in class. No, Rachel, I enjoyed having you in class. You were the skateboard meister. So that's one of the reasons I like teaching. All right, here's your question. Now, this is a little different from homework 16, number 5. This one's equal mass. So you got 100 grams of substance J, and it's at 500. A little bit different number. And you got 100 grams of substance U, and it's at 300 Kelvin. Okay? So different initial temperature. So you got 500 Kelvin up here, 300 down here, and you got 100 grams of each. And oh, by the way, jot down the specific heat. You're going to need it. Okay, 0.84 for substance J, 0.84 calories per gram Kelvin. And for substance U, it's 0.56 calories per gram Kelvin. And there's a little schematic diagram of J and U in contact. You can think, the original picture was a beaker with a blob of substance U in the beaker. But answer me this, riddle me this. Are they in equilibrium or no? Go ahead and vote. Because this is the first question. You're trying to figure out a thermal equilibrium temperature from 2 substances. First thing you got to recognize is, are they actually in equilibrium already, or are they out of equilibrium? So what do you look at? Okay, go ahead and answer. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let me see what you guys voted for here. Okay, yeah. Option B is correct. They're not in equilibrium because their temperatures are different. One's 300, one's 500. Okay, so that's the most basic thing you got to ask yourself. All right, are they in equilibrium? If they're not, then you got more things to decide. Here's question 2. All right, same preamble, 100 grams of each, 500 and 300 thermal contact, same specific heats. Which one cools, which one warms up? Or do they both cool down? Or do they both warm up? Read carefully. And make sure you make a note of the question. Or at least in this case, your answer. Because this will be important when we get to the calculation. Because the calculation, you're going to be putting together several concepts, and you got to keep it mentally organized. And that's sometimes, no offense, but keeping stuff mentally organized is sometimes half the battle. And not just for you guys, this is half the battle for us regular scientists that do it every day. You know, we're not doing this stuff every day. We're doing other fancy stuff, but, you know, you still got to keep your mental equipment organized. And remember, as we go through these questions, if you're sitting with a friend, it's perfectly fine to talk things over. Okay. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see. The answer is B. Yeah. So thermal contact, the one that starts hotter cools down a little bit. That's substance J at 500 Kelvin. And the one that starts cooler is going to warm up a little bit. Right? But you still got other things to decide. So let's go to the next question. Make sure you jot down the correct answer here if you didn't get it, which most of you got it, but some of you didn't. Some of you voted for C. Substance J warms up. And answer C is not physically the way the universe works. Because the kinetic energy model, you're not going to get extra net kinetic energy out of the cold. You're going to get it out of the hot. So it doesn't go in the direction of interaction or option C. Next question. Kelvin for Kelvin, which one's easier or harder to warm up? And hopefully you'll know what to look at for this one. You're going to decide this. When you're trying to figure out, is my equilibrium temperature righteous? Does it make sense? This is something that you got to think about. You know, which substance is easier to cool off? Which one's easier to warm up or cool down? You know, so you got to kind of mentally have an idea of the answer to this. So make sure you write down the correct answer here as well. 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, pretty good. Kelvin for Kelvin, substance J. And here's how, go ahead and write this down in your notes. The reason that this is true is you have the same amount of grams, right? And substance J has a bigger specific heat, 0.84. You know, so every one of those grams to go up by a single Kelvin, 0.84 calories. But substance U, a little bit easier. You know, it only needs 0.56 to go up, or to go, it has to lose, 0.56 to go down. But substance U is going to go up. Substance J is going to go down, so it has to lose 0.84 calories for every gram and every Kelvin. That's what the specific heat tells you. And if you recall back to when we talked about specific heat, and on homework and stuff, I usually use the phrase gram for gram and Kelvin for Kelvin, which substance is easier to heat up. That tips you off to look at the specific heat. All right? In the table. This is not exactly the same. I don't use that language. I do use Kelvin for Kelvin, but I don't use gram for gram. But what I do have is the same number of grams, 100 and 100. So this is equivalent. So if you have the same number of grams, or if you just consider 1 gram at a time, gram for gram, look at the specific heat. Daniel. Yeah, and we do change the amount of grams. And homework 16, number 5, does have 120 grams for one substance, 200 grams for the other. So we're going to take that into account. But I mean, this is a basic version of a decision that you've got to make. All right. Now I'll talk when we get up to the document cam and work through the calculation by hand. I'll go through what happens with the homework problem. Any other questions? Because we'll use it when we do the homework problem, number 5 all the way. I'll discuss that very question that you brought up, Daniel. Okay. All right. Next question, and this is the kicker. They exchange 100 calories. All right, so this thing's insulated. So it's not getting any energy from outside. It's inside a styrofoam container. So no sunlight is, beaming in. You don't have it on a burner or anything. It's just on the counter. It's insulated with styrofoam. So if substance J cools off, it loses energy. The only place for that energy to go is into substance U. So this one, the question is a little bit more subtle. Does substance J dip by more kelvins than substance U rises? Or is it the other way around? And this question, I want you to write down the answer very carefully and add the fact that they exchange 100 calories. So minus 100 calories for substance J and positive 100 calories for substance U. Also in your notes, jot down the master equation for deciding this. Q equals MC delta T. We've been using that since last week. And we're going to use it in a few slides here when we get to the document camera. Q equals MC delta T. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let me get the right answer marked here. The correct answer is substance J. All right, now this one, here's how you can think of it. 100 grams of substance J, every gram of substance J requires 0.84 to dip down by a Kelvin. All right, so if you have 100 grams of it, it takes 84 calories to dip down by 1 Kelvin for substance J. All right, so if substance J loses 84, it'll dip down by 1 Kelvin. But now substance U, 100 grams of it, its specific heat is 0.56. 100 grams of it, it only needs 56 to warm up by a Kelvin. So when substance J dips by 1 Kelvin, it's going to send all that energy over to substance U, and that's more than it needs. It only needs 56 calories. It's sending 84. So substance U is going to go up by 1 point something. And you can figure it out. They're not going to be the same. And this concept is this is now getting to the nitty-gritty of how you decide the thermal equilibrium temperature. All right? Let me ask you this, and this is a mental, I don't have it set up for clicking, but let me ask you this, and raise your hand if you have an idea for your answer. The thermal equilibrium, since B is correct, the thermal equilibrium temperature, is it going to be at the halfway temperature, 400 Kelvin? Are they going to meet? They're not going to meet halfway. Okay, so we know that they're not going to meet halfway because they're different substances. If it was hot water and lukewarm water, then yeah, 100 grams of each, then yeah, you'd go right to the midway temperature. But these are different substances. One's easier to warm up, one's easier to cool down. All right? So, mental IQ test question number 2. The equilibrium temperature for this system, above 400 or below 400? Closer to 500 or closer to 300? Raise your hand if you have an idea. What do you think? Why? You say closer to 500. Why do you say that? That's right. Substance J is dipping. For every calorie exchanged, substance J dips, but not by much. And substance U really dips upward by quite a bit more. So there's your answer. Now we're going to apply that when we go to the document cam in a second. So let's just recap the specs for this problem. All right. So we're dealing with 2 different substances, and here's a little schematic for the 2 substances, J and U, in thermal contact. All right. And they start with different temperatures. They're out of equilibrium. And the ones that we have are 359 and 279. And I'll write all this stuff down here in a second, so don't worry about that. And also, we're going to do different masses now for this one, all right? And that'll affect, that'll also affect where the equilibrium temperature ends up. Is it above the midpoint or below the midpoint? And we don't just have different substances, we also have different masses. But you can calculate it. It's not too bad. So there's a lot to keep together, keep it mentally organized and stuff. And let's go to the document camp. So let me pause the YouTube here now. And okay, we did a great job with that, and I'll be. Shh. Do you guys want to dismiss early or what? Go home and eat your trick-or-treat candies? Okay, I'll be putting up this and you know what? Look at the other class's PDF. You know what we used in the other class? Plus or minus 200. And that's why I wanted to use plus. I was glad that somebody selected 30, because then we would use plus or minus 300 in this class. But take a look at the other classes' talking PDF. Now your homework is going to be thermal equilibrium calculations plus a little bit of reading forward in Chapter 7, so maybe a little vocab. Also, we're now done with Chapter 6, and so I'm going to activate the Chapter 6 mini-review, and it will be due November 20th. All right? Because it's a review assignment. All right? But homework 17 will be due on Tuesday. All right? You're dismissed. I'll see you.